This video is about CDPs for crooked lines, but it is also about CDPs for straight lines, and it includes information on how to flex those CDPs if you choose to do that.
In this video, I discuss how to use the SuPro CSV, SuNear CSV, and SuFlex 2D programs. The SuPro CSV program creates a set of coordinate locations usually called a CDP profile. The profile can be straight, slightly bent, crooked, or even intersecting itself or coiling over itself. The SuNear CSV program uses coordinates to assign each input trace the CDP number of the closest CDP profile location. The SuFlex 2D program examines each CDP and duplicates traces from neighboring CDPs to fulfill a desired distribution of offsets. Also included is using SuBin CSV to compute CDP numbers without a profile, just using shot and receiver station or point numbers. Now, the programs discussed here are not limited to 2D or crooked profile situations, but this video concentrates on that. This is a plot of the receiver locations of a survey that contains some bends. Close-up of the same survey. Note again that this is a plot of receivers only. A CDP profile created by program SuPro CSV. Each red dot is the center coordinates of a CDP. This CDP profile was created using receiver locations. Only the receivers. This is the setup that produced the CDP profile. First, the SuTool CSV program is used to convert a standard SPS2R file into a CSV Q file. Only that Q file is input into SuPro CSV to produce the CDP profile. The SuPro CSV program outputs the created CDP profile into another Q file. You do not have to use an input SPS2R file to create the CDP profile. Both SuTool CSV and SuPro CSV allow many ways to create the CDP profile. This is a view of the input SPS2R file and the Q file that SuTool CSV makes from it, and the CDP profile Q file produced by SuPro CSV. Note that the Q file output by SuPro CSV now has the CDP number right after the leading Q on the records. All the other values come from the input file, but have been modified according to the option used in SuPro CSV setup. Let's look at the options used in SuPro CSV to produce the profile. The chordai parameter is set to 12.5, which is the CDP interval that we want. The receivers in this survey are 25 meters apart, so 12.5 is a good choice for CDP interval. Note, this parameter's name derives from the concept of chopping or cutting tree trunks into cords of wood for burning in fireplaces. A little British Columbia flavor there. Okay, the chordai parameter simply creates points at 12.5 meter intervals along the receiver line. Since the receivers are approximately 25 meters apart, there are approximately twice as many points after chordai. Next, the Nmax parameter simply averages together 30 of those points. This causes a rounding off of the bends in the line. By default, another parameter smooths those points. Then, also by default, those averaged and smooth points are chorded again into 12.5 meter intervals. This final chording is needed, otherwise the averaging and smoothing would make the points near the bends closer together. This is a plot of the receivers and the midpoint locations of all traces in this survey. The midpoint locations come from the actual trace headers. You can see how to make this plot using scripts in the demos directory. This is a fake seismic survey which you can create using other scripts in the demos directories. This fake survey has the shots located along the same line as the receivers. As long as the shots are located along the receiver line and occur at regular intervals, the midpoints will look as seen here. Here, the midpoints are colored in 3 offset ranges. Purple midpoints are smaller shot to receiver offsets, green are middle offsets, light blue are larger offsets. Note that at the bends in the survey, smaller offsets are near the survey line and larger offsets are further away from the survey line. Note also that along straight parts of the survey, all midpoints are on the line no matter what their offset distance. Now, the CDP profile that was created previously is also plotted. Note that CDP profile goes through the center of the midpoints near the bends. This occurs because the NMAX average parameter is 30, and the shots in this survey are split spread with 30 traces on each side. But it is not necessary to get the NMAX average so that it goes through the center of midpoints. Here it is set to 10. This results in a CDP profile which stays closer to the survey line at the bends, and also stays closer to the midpoints that have smaller offset distances. Here, the NMAX average is set to 50. This results in a CDP profile which is further away from the survey line at the bends, and also stays closer to the midpoints with larger offset distances. Remember that these CDP profiles are created just from the receiver locations. The SuPro CSV program is simply creating points at 12.5 meter intervals along the receiver line, then averaging and smoothing using some neighboring points on both sides of each created point. Crudely speaking, this has the effect of rounding off the bends in the input receiver line. With a bit of thinking, you should understand why a value of 30 for NMAX average for a split spread survey with 60 traces per shot will produce a CDP profile which is near the center of midpoints in the bends. But there is nothing magic about having a CDP profile in the center of the midpoints. It is just a reasonable position. This symmetric averaging is done for all values in the Q records, not just the coordinates. You may find this averaging useful for elevations or statics or other values. This is a plot which contains the entire CDP profile. Note that it extends beyond the ends of the receiver line. Extending the CDP profile is done automatically in SuPro CSV since it simplifies and speeds up the program code. An extended profile also has the benefit of accommodating surveys where some shots are located beyond the ends of the receiver line. After deciding which CDP profile to use, the next step is to use SuNear CSV to assign each trace to the CDP that is closest to. The SuNear CSV program inputs the CDP profile and the traces. For each trace, it finds the profile coordinates which are nearest the midpoint coordinates of that trace. Note options MGX and MGY. These options exist because Seismic Unix trace headers do not contain midpoint coordinate values. The MGX and MGY options compute the midpoint coordinates from the trace header, shot, and receiver coordinates, but then look for the receiver coordinate names in the CDP profile file. Since it's also possible to create CDP profiles from shot locations, there are similar options for when the shot coordinate names exist in the CDP profile file. This plot shows the midpoints of only 3 CDPs after SuNear CSV. Same plot enlarged. Since the traces are assigned the CDP they are nearest to, you should expect the CDPs to contain traces in this kind of spatial distribution. Note here that these CDPs are not cells or bins. These CDPs have no distance limits. The cross-line distance between a CDP center and the trace could be infinite. The inline distance between a CDP center and a trace is limited because of the previous and next CDP centers. After finding its nearest CDP, the inline and cross-line distances of each trace are computed and output in trace header keys IGI and IGC. The green plot is the cross-line distance versus the CDP number of all traces. Below that, the receiver locations are plotted at approximately the same scale. Since the CDP profile has been extrapolated beyond the ends of the receiver line, you might expect more CDPs here. But this plot only shows the CDPs that actually have traces. This plot of the cross-line distance is easy to understand, but probably a lot less useful than the same plot of the inline distances. This is a plot of the inline distance versus the CDP number of all traces. The inline distances are relative to the CDP centers, with positive being in the direction of the next higher CDP number. Since the CDP interval is 12.5 meters here, these inline distances will be between plus and minus 6 meters. An enlarged plot of the inline distance versus the CDP number for all traces. Note that the inline distances are put in the IGI key, which is an integer. So there is a granularity of 1 meter in this plot. Notice that the left side of this plot shows inline distances of about 0, while the right side shows inline distances of about 5, but some inline distances of minus 6. To understand the significance of these inline distances, the next two plots will show just traces with small shot-to-receiver offsets. This is the left side of the CDP profile with just midpoints of traces that have smaller offsets. Note that the red CDP center profile points are in alignment with the green midpoint locations, even covering many in the plot. This is the right side of the CDP profile with just midpoints of traces that have small offsets. Note that the red CDP center profile points are not in alignment with the green midpoint locations. Parameters of SuPro CSV allow you to shift the CDP centers along the profiles so that the midpoints become more aligned with the CDP centers. The shift is achieved by small changes in the CDP interval. The new improved alignment at the right end of the profile. Note here that the right side of this plot now shows alignments closer to 0. Also remember that in the original alignment, these CDPs have some traces with inline distances of minus 6 and some with plus 5. This means that after shifting, individual CDPs now consist of traces that are closer together in the inline direction. So you can expect stacks of these CDPs to be more focused than using the unshifted profile. Inline distances from both profiles. Note that this same kind of shifting can be done elsewhere in the profile. Generally, trying to align CDPs near line bends may be pointless. My advice is to concentrate on straight sections. You can, of course, not perform any alignment. Or you can, of course, align with middle offsets or larger offsets rather than smaller offsets. But there are several reasons in favor of alignment with smaller offsets. 1. Smaller offsets are less affected by velocity errors. 2. Smaller offsets are less affected by dip. 3. Smaller offsets have smaller Fresnel zones. That means that alignment with smaller offsets probably makes each CDP a slightly better representation of the subsurface directly beneath it. Later in this video, there is a discussion of SuFlex 2D, which may give you more insight into whether you want to align your profile. Here I point out that the inline and crossline distances in IGI and IGC keys can be limited by a simple use of the SuWind program. This is a plot of midpoints after only retaining traces with crossline distances of minus 40 to plus 40. A result of this that might be slightly surprising is that this will cause the top of a stack to look ugly. This occurs because this crossline range eliminates the small offsets near the bends. and so the mute zone drops down further into the stacked data. In general, if you are trying to get the best focus of a target offset range, you need to consider the offset distance range, the crossline distance range, and where you located the actual CDP profile points. Also, if, for some reason, you want rectangular CDP areas, you can achieve this by using another SUN to limit the inline distance values. This is a plot made by a test job in the demos Geom3D SuPro CSV directory. The red X's are a profile which intersects itself. The green triangles are some midpoint locations which we want assigned to CDPs in the horizontal section of the profile. But a problem happens at the intersection. The midpoint near the intersection gets assigned to a CDP along the vertical section of the profile. This occurs because that particular CDP is closer to the midpoint. For an actual survey with an intersection, many midpoints near the intersection could have this problem. This problem will also occur if parts of the profile just get near each other. This is a setup of SuNear CSV which can solve the self-intersecting profile problem. Along with the usual XY coordinate dimensions, another dimension is specified. This is the dimension which is used as a range. As set up here, this dimension uses receiver station in the input profile file to restrict the range of the profile that each trace will consider when finding the nearest CDP location. For each trace, the midpoint station number is computed, and only sections of the profile within 30 stations will be considered for finding the nearest CDP. Of course, for this to work, the profile file must contain at least an approximate station number. Profiles generated from standard SPS2R files or SPS2S files should have usable station numbers. A small representation of a coil survey. Typically, these surveys are streamer cable marine acquisition. With some effort, you could create a similar coiling profile from the shot records in a UCOA P190 or P184, or even an OGP P1-11 file. Probably the easiest way to start is to extract the S records from those files using the Linux sed command. After that, SuTool CSV or a spreadsheet program can produce the Q file to input into SuProf CSV. This situation would require a third dimension to restrict the range to parts of the coil, similar to the restriction dimension needed for a self-intersecting profile. There are no station numbers in this situation, but other range values might exist. Primary candidates for the range dimension are the shot record number or the shot acquisition time, which usually exists in the UCOA S records. Using these values would require larger range limits because they are not midpoint values. That is, even the furthest trace of a shot has the same shot record number as the first trace. Since coil surveys are 3D surveys, you might wonder why you would want to use SuProf CSV and SuNear CSV. But these programs can actually do more than assign CDP numbers. They can, for example, update ocean water bottom pick times or depths along the coil. More generally, streamer cable 3D acquisition is often treated like 2D for early parts of the data processing flow. So you might find these programs useful even for 3D. Before continuing, here is a good place to show some additional functionality of the SuProf CSV program. Rather than reading an input Q file, you can just directly specify the dimension values via parameters. In fact, this is the specification that created the previous self-intersecting profile containing X, Y, and station numbers. A similar specification was used to produce the coil profile. The next plots compare the use of a profile to assign CDPs versus a much simpler technique that computes CDP numbers from station numbers. In standard SPS2 files, the shots have a station number and the receivers have a station number. The SuGeom CSV program can copy these station numbers into the geoentlof and GAPS trace header keys. Since there are usually 2 CDPs per station, then this simple SuBin CSV setup will compute CDPs for traces. Note that the -112 value is simply a starting constant that makes it easier to generate the next plots. Here is a comparison of the CDP fold between proximity to profile and computation from station numbers. This is not surprising. CDPs computed from stations are pretty much what you see when first learning seismic data processing. You see nice stacking charts and well-behaved offset distributions and fold values, and midpoints all occupying the same coordinates within their CDPs. But that only occurs for perfectly straight lines with shots and receivers located at exact intervals along the line. Using station numbers essentially replicates that nice simple situation. Of course, this is not actually true. The traces of CDPs computed from stations will actually have dispersed midpoint coordinates and offset distances. But often, even for crooked lines, it is reasonable to use station numbers to compute CDPs because sometimes consistent fold is most important. Your situation determines which method to choose. Here are plots of the midpoints for 3 CDPs assigned by proximity to profile and 3 CDPs computed from the station numbers. Which is better is hard to say. Another comparison of 3 CDPs. Note here that using proximity to profile produces a tighter group of midpoints for the CDPs. Also, each CDP set of traces is angled better with respect to the local line direction. Again here, the proximity to profile CDPs form a tighter group and have more desirable angle with respect to the local line direction. Here is a setup for the SuFlex 2D program. This program examines the offset distribution inside each CDP and duplicates traces from neighboring CDPs if some offsets are missing. Those duplicated traces from neighboring CDPs have their CDP number changed to the CDP number of the CDP being examined. This means those duplicated traces will be part of that CDP gather and stack. Note that only the CDP number and the inline distance IGI key value are changed in the duplicated traces. This means, for example, if you put the output traces back through the SuNear CSV program, the duplicated traces would be reassigned back to their original CDPs because their coordinates have not changed. If you want to know which traces are duplicates, look at the output IGI key values. The IGI add parameter causes a constant to be added to the output IGI key values of duplicated traces. This allows the SuWin program to delete the duplicates if you choose. You may wish to delete the duplicates after some programs have processed these flexed CDP gathers. That is, some processes benefit from having nice offset distribution within CDPs, so flexing can help those processes, and then you can get rid of the duplicated traces. This diagram helps to understand what happens during flexing. The X's in this diagram represent traces. The horizontal direction shows 3 CDPs. The vertical direction is the offset bin number of the traces. To flex CDP n, by default, only CDPs n-1 and n+1 are considered. Note that the third offset bin of CDP n only has one trace. A trace from either CDP n-1 or CDP n+1 will be duplicated, and the duplicated trace's CDP number will be changed to n before output. Which trace does SuFlex 2D choose to duplicate? Well, by default, that is determined by the inline distances put into the IGI traceheader key by SuNear CSV. Note that offset bin 5 of CDPN also only has one trace, so a neighboring trace would be duplicated. But offset bin 7 would continue with just one trace because it has no neighbors available for duplication. Note also that offset bin 4 has 3 traces. The SuFlex 2D program gives you the option choice whether to output all 3 in that offset bin or just the best 2 traces. I want to point out here that each CDP is flexed without considering what duplications happened in the previous CDP or what duplications will happen in the subsequent CDP. A consequence of this is that the same trace might be duplicated into its 2 surrounding CDPs. The previous diagram was for illustrative purposes. Here is a more realistic diagram. If a survey is split spread acquisition, there are often 2 traces in every offset bin. And when shooting on the same locations as receivers, those 2 traces will have exactly the same inline distances and exactly the same offset distances. This diagram shows that. Notice also how the traces are actually not aligned with the CDP centers. The alignment is not random because the distance between midpoints is roughly half the receiver spacing, and the distance between CDPs is also roughly half the receiver spacing. Therefore, in straight parts of lines, it is logical that however any CDP is aligned with its midpoints, then the nearby CDPs will also be aligned the same way with their midpoints. A consequence of this local alignment is that trace duplication will often favor the next CDP in some parts of the profile and the previous CDP in other parts. Note, for instance, in the diagram, that CDPN offset bins 3 and 5 will both choose to duplicate traces from CDPN+1 because the local alignment means its traces are closer to the center of CDPN. This local direction favoritism may have unexpected effects. A good quality control test is to sort all traces back to shot gathers. Remember, trace duplication has not changed the shot numbers. So, after sorting back to shot gathers, if you find particular shots now have a lot more traces than they started with, then you should investigate why this much duplication occurred for that shot. This is the CDP fold before and after flexing our crooked profile survey. You can see that the CDPs in the bends now have typical fold. A better comparison here. The irregular coordinates of this survey often cause the largest offsets to change along the line. This is particularly true near bends, of course. Here, traces with offsets greater than 650 meters were deleted. This gives a better comparison of the effects of flexing. Here is a plot of the fold with CDPs computed from station numbers. All traces of 4 shots have been removed, causing a decrease in the fold near CDP 520. A plot of the fold after flexing. This plot shows that SuFlex 2D still functions even when the traces have not been through the SuNear CSV program. Since all IGI key values are 0 here, when it needs to duplicate a trace, SuFlex 2D uses the first trace in the correct offset bin from the neighboring CDPs. A reminder that SuPro CSV and SuNear CSV can be used for other purposes beside profiles. A bit of advice when considering using these programs. I include documentation here just so you can read it conveniently. I do remind you that the documentation may change after this video.